Open Stax Chapter 5 continued, Section 5.2, Waves and Wavelengths. Visual and auditory stimuli both occur in the forms of waves. Although the two stimuli are very different in terms of composition, waveforms share similar characteristics that are especially important to our visual and auditory perceptions. In this section, we describe the physical properties of the waves as well as the perceptual experiences associated with them. Amplitude and wavelength. Two physical characteristics of a wave are amplitude and wavelength. The amplitude of a wave is the distance from the center line to the top point of the crest or the bottom point of the trough. Wavelength refers to the length of a wave from one peak to the next. Wavelength is directly related to the frequency of a given wave form. Frequency refers to the number of waves that passes a given point in a given time period and is often expressed in terms of hertz or cycles per second. Longer wavelengths will have lower frequencies and shorter wavelengths will have higher frequencies. Light waves. The visual spectrum is the portion of the larger electromagnetic spectrum that we can see. As Figure 5.6 shows, the electromagnetic spectrum encompasses all of the electromagnetic radiation that occurs in our environments and includes gamma rays, X-rays, ultraviolet lights, visible light, infrared light, microwaves, and radio waves. The visible spectrum in humans is associated with wavelengths that range from 380 to 740. A very small distance, since nanometers is 1/billionth of a meter. Other species can detect other portions of the electromagnetic spectrum. For instance, honeybees can see light in the ultraviolet range, and some snakes can detect infrared radiation in addition to more traditional visual light cues. In humans, light wavelength is associated with perception of color. Within the visible spectrum, our experience of red is associated with longer wavelengths. Greens are intermediate, and blues and violets are shorter in wavelengths. An easy way to remember this is the mnemonic Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. The amplitudes of light waves is associated with our experience of brightness or intensity of color, with larger amplitudes appearing brighter. Sound waves. Like light waves, the physical properties of sound waves are associated with various aspects of our perception of sound. The frequency of a sound wave is associated with our perception of that sound pitch. High-frequency sound waves are perceived as high-pitched sounds, while low-frequency sound waves are perceived as low-pitched sounds. The audible range of sound frequency is between 20 and 20,000 hertz, with greatest sensitivity to those frequencies that fall in the middle of this range. As was the case with the visible spectrum, other species show differences in their audible ranges. For instance, chickens have a very limited audible range, from 125 to 2,000 hertz. Mice have an audible range of 1,000 to 91,000 hertz. And the beluga whale's audible range is from 1,000 to 123,000 hertz. Our pet dogs and cats have audible ranges of about 70 to 45,000 hertz and 45 to 64,000 hertz, respectively. The loudness of a given sound is closely associated with the amplitude of the sound wave. Higher amplitudes are associated with louder sounds. Loudness is measured in terms a logarithmic unit of sound intensity. A typical conversation would correlate with 16 decibels. A rock concert might check into 120 decibels. A whisper 5 feet away or rustling leaves are at a low end of our hearing range. Sounds like a window air conditioner, a no more conversation, and even heavy traffic or a vacuum cleaner are within a tolerable range. However, the potential for hearing damage for about 80 decibels to 130 decibels. These are sounds of a food processor, power lawnmower, heavy truck, subway train, live rock music, and a jackhammer. The threshold for pain is about 130 decibels, a jet plane taking off, or a revolver firing at close range. Although wave amplitude is generally associated with loudness, there is some interaction between frequency and amplitude in our perception of loudness within the audible range. For example, the 10 Hz sound wave is inaudible no matter the amplitude of the wave. A 1000 Hz sound wave, on the other hand, would vary dramatically in terms of perceived loudness as the amplitude of the wave increased. Of course, different musical instruments can play the same musical note at the same level of loudness, yet they still don't quite sound quite different. This is known as the timbre of a sound. The timbre refers to a sound purity, and it's affected by the complex interplay of frequency, amplitude, and timing of a sound wave.